In the previous part, we looked at naive Bayes classification algorithm and how to use scikit-learn to apply this algorithm. Let's see another popular classification algorithm with many use cases in accounting and finance. Bankruptcy prediction, business failure, fraud detection, financial statement audit are just a few examples. Support vector machine is a popular algorithm invented by Vladimir Vapnik. What SVM do is to find a separating line, or more generally called a hyperplane, between two classes. Suppose we have some data of two different classes. Support vector machine is an algorithm that takes this data as an input and outputs a line that separates those classes if possible. Let me give you three lines, A, B, and C. Which line do you think separates the data, A, B, or C? Pause the video and type your answer in the comment section. And obviously, line A over here that separates on one side the X's, on the other side the O's. That was easy. Let me do this again. Here is a new data set and I give you three lines again. This line over here A, this one over here B, and this one over here C. Select the line that you think best separates the data. Obviously, all three seems to separate the data, but one is the best. Pause the video and type your answer in the comment section. I would say the line A is the best separator. Why is this so? What line A does that the other ones don't do? Maximizes the distance to the nearest point and does this to both classes. So it is a line that maximizes the distance to the nearest points in either class, and that distance is often called margin. It is a good to know the word margin because it is the thing that is being maximized. It is important to know some terms in SVM and other AI algorithms because even if you are not writing AI code, there are chances that you will be involved in the implementation of AI as a business process owner. It is highly recommended that managers and departments heads' recommendations and their feedbacks should be factored in the AI implementation process because they have domain business knowledge. So having some understanding of AI terms help them talk to IT professionals in the same language. So the margin is the distance between the line and the nearest point of either of the two classes. Let me give you three linear separators for the same data set to ensure you got this right. Which one do you think maximizes the margin? A, B, or C? It is the middle one, B. There is a really large margin to the blue dataset, but a small margin to the red X over here. So it doesn't really maximizes the margin to both dataset. Just that's the one. And the same is true for line C on the right side. So the reason why we pick the one in between, it seems to be most robust to classification mismatch or classification error. If you pick a line that is really close to existing data, then a small amount of variation, irregularity, or more appropriately called noise would make the label over here flip and it feels not very robust. So the inside of the support vector machine is to maximize the robustness of your result. Suppose this over here is your data. Which of the two lines do you think maximizes the margin and would be the correct result of support vector machine? This question is tricky. It is either this line or this line. It is actually this line B over here, and you might have gotten this right. Now this line A does maximizes the margin in some sense to all the data points, but it makes what is called a classification error over here, this red X. The red X is on the wrong side of the green line, whereas in this case of line B over here, all the points are classified correctly. Support vector machine puts the correct classification of the label first and foremost, then maximizes the margin. If we didn't care about the correct classification, then this line back here has even a larger margin to all the training examples. That's obviously the wrong line. So for support vector machine, you are trying to classify correctly, and subject to that constraint, you maximize the margin. Sometimes it seems impossible for support vector machine to do the right job. For example, you might have a data set just like this, in which clearly no decision surface exists that would separate the two classes. You can think of the point down here as an outlier. The best you can do might be to make a decision boundary just like this and just denote the fact that the one point is on the other side. Support vector machines often find the decision boundary that maximizes the clearance to both dataset and tolerate at the same time individual outliers as shown over here. So now it is time to head to Google and find sklearn support vector machine. Just click on this one. The first thing that I see is there are some advantages and disadvantages to support vector machine. Those points that we will revisit a little bit later in this course, but I want you to look at the coding. So the first thing, it gives me classification. I can see that there is already an example code that is ready to go. This is starting to look a little bit familiar now. So I have my import statement with SVM, I have my training features, and I have my training labels like I did in a last example with naive Bayes. I create my classifier. This looks slightly different as it has an additional class SVC. I will explain it later in the video. For now, let's continue with the next lines of codes. Here, fit it using training features and training labels, and then down here, they have shown us how to make a prediction. So as you can see, it is exactly the same few lines of code. So instead of now saying Gaussian naive Bayes, I'm calling it an SVM. And this is one of the things that is nice about scikit-learn. It always going to be the same syntax. We have already seen in the naive Bayes video how we have done all the above steps and came up with a prediction of number 1, which we understood as by recommendation by the algorithm. I won't repeat the same for SVM in this video. Instead, I will take you a bit deeper into the algorithm settings. Now I want to show you something really interesting that will make it immediately clear how powerful SVM can be. So what I'm showing you here are two different SVMs. These are the same examples that I used in the previous naive Bayes video. Stock recommendations. You don't know how I prepared these yet, but we are going to spend a lot of time talking about this. You can see an SVM can do some really complicated shapes to the decision boundary, sometimes even more complicated than you want. So let's talk about some pretty interesting insights as to how this is coming out of as a classifier. Remember, the SVM is a classifier that is built on giving us linear separation, a straight line. So how on earth can it give us this non-linear decision boundary? I'm going to give you a very tricky data set. There are a couple of red axes and I have clustered around the origin of this coordinate system X and Y. And there are whole bunch of O's that lie more on the edges. And based on what you have learned so far, do you think support vector machine give you a linear separation here? Yes or no? And based on what you have learned so far, I would say no is the correct answer. There is just no good linear hyperplane or linear separator between these two classes. Or put differently, it is really hard to draw a line between these two classes. But in reality, the answer is yes. Now we are going to learn a trick that would change your answer from no to yes, and that trick relates to features. Recall, what does it mean by features and labels? Features are the inputs and label are the outputs. So far we have assumed that we input our data features X and Y into this magic black box called support vector machine, and it out comes a label where labels either a blue circle or a red X. But we can create new features from existing features. So we are going to pick a feature that is helpful for my example here. It's going to be X square plus Y square. Why is that? You will see in a minute, but I can convince you that it is easy to compute X square plus Y square from X and Y. I know that most accountants are not good in this type of mathematics, but I will explain later in this SVM video why it is so useful for the next generation of accountants. We will touch in more details later in this course about features and creating new features from the existing one. So now I have three-dimensional input space and it is hard to draw over here. And I can run the exact same algorithm on these three features that I previously ran on the two features. And now here is my question to you. Do support vector machines work now? Or in other words, is this new situation linearly separable? By which I mean, can we find the line or a hyperplane that separates the axis from the circles? If this is now an official space. And the answer is yes. And it takes a little bit of time to understand why. Let's call this new feature over here Z. So we know that Z equals X square plus Y square. And we are trying to learn a hyperplane between X, Y and Z. Z is always non-negative because of the distance to the origin. And for all the rate points, the distance to the origin is small. And for all the blue circles, distance to the origin is large. So we show the exact same data in this new projection of X and Z, omitting Y. I find that all the red axes have a same value of Z, whereas all the blue circles have a larger value of z. And just to understand this, z measures the distance to the origin. So here is a small z, here is a small z, here is a small z, here is a small z. And for the blue circles, the distance is large, as you can see over here. So if I map the data into this new coordinate system with z, you find all the blue circles have a larger value of z and all the red axes have a small value of z. So you look at the data in this new coordinate system with x and z. Is this data linearly separable? Yes or no? And I would say the answer is yes. Here is the line. And what is really interesting, this line over here in the original data corresponds to a circle. The circle of equal distance to the origin in the coordinate system. So as we added this new feature, we are able to use support vector machine to learn non-linear decision surface in the form of a circle. This is quite amazing. The main point here is that there is a feature transformation going in the SVM, which will change the way you think about linearly separable data. Now let me stop you here to give you some breathing space. In the next video, I will continue with SVM and I will discuss why all of this going to be useful for next generation accountant.